morning and good night, everyone. Today we'll be reviewing everything you need to know from your atomic theory and periodic table, from history of the atom to chemical families and trends across the periodic table. By the end of this video, hopefully you'll be able to understand how scientists helped shape our view of the atom and how those tiny particles explain the patterns we see in a periodic table today. So grab your notes and let's jump right in. Our story starts with Democritus around 400 BCE. He was the first to suggest that all matter was made small, indivisible particles catomous, meaning uncuttable. He didn't do any experiments particularly, however, this is pure logical reasoning from his mind. He figured if you kept cutting matter smaller and smaller, eventually you'd reach something that can no longer be cut. And that's called the atom. His model was a solid sphere, tiny indestructible balls that made up everything around us. Next up is John Dalton. He turned Democritus's philosophy into a real scientific theory with experiments. Dalton studied gases and chemical reactions and realized atoms combine in fixed ratios. He created three major laws. Law of conservation of mass. Atoms aren't created nor destroyed. The law of definite proportions. Compounds have set ratios. And finally, the law of proportions. Same elements can form different compounds like CO and CO2. This model was called the Billard-Bell model, solid spheres combining to form compounds. Dalton thought atoms were solid, but Thomson discovered something shocking: electrons. Using his cathode ray tube experiment, he passed electricity through vacuum and noticed the beam bent towards the positive plate, meaning it had a negative charge. He concluded atoms are divisible and contain electrons. This model was called the plum pudding model, a positively charged pudding with electrons scattered like raisins. Then comes Ernest Rutherford. He performed a famous gold foil experiment, firming positive alpha particles at thin gold foil. Most went through, but a lot bounced back, meaning that there was a dense center. He discovered the nucleus and that atoms are mostly empty space. His nuclear model showed electrons orbiting a small positive nucleus. Niels Bohr took Rutherford's model even further. He discovered electrons move in fixed energy levels or orbit around the nucleus. Using the hydrogen emission spectrum, he noticed hydrogen gave off specific colors, meaning electrons jump between energy levels when they gain or lose energy. His planetary model showed electrons orbiting like planets around the sun. Next is Erwin Schrödinger. He discovered electrons don't move in perfect orbits, they become like waves. He used complex math to find where electrons are most likely to be, not exact paths. This formed the quantum mechanical model or electron cloud model, showing electrons and probability zones called orbitals. Finally, James Chadwick discovered the neutron, a neutral particle inside the nucleus. He bombarded beryllium with alpha particles and saw radiation that knocked out protons, providing neutrons exist. His modern atomic model includes protons and neutrons inside the nucleus, surrounded by an electron cloud. So over time, we went from solid spheres to complex quantum math, proving science is always evolving. Let's recap the main three subatomic particles. Protons, which have a positive charge inside the nucleus and a mass of 1 AMU. Neutrons, no charge in the nucleus and a mass of 1 AMU as well. And then finally, electrons. They have a negative charge, are found outside the nucleus and almost have no mass due to how small they are. Some key equations to note is that when calculating ions and isotopes, we use these said formulas. Charge is equal to protons minus electrons. The mass number is equal to the amount of protons as well as neutrons collected. And neutrons are equal to the mass number minus the atomic number. And remember, relative atomic mass is the percent of a decimal times the mass of an isotope. Next, let's break down the chemical families on the periodic table. We're going to dive into their specific categories and how they all tie into each other. Our first group is alkali metals. These metals are found on the very left-hand side except for hydrogen. They're super reactive, especially with water, form +1 ions, and soft, shiny, and low density. These examples include lithium, sodium, and potassium. Our second group is alkaline earth metals. They're super reactive, but a little less than alkali metals. They form +2 ions, and these examples include magnesium and calcium. Next is our transition metals, which are found from groups 3 to 12. They're found in the middle, shiny, malleable, and conductive, can form multiple positive ions, and some examples of this are iron and gold. Next are post-transitional metals. They're soft and have low melting points. Some examples include tin, lead, and bismuth. A more unique group is called metalloids. They form a zigzag pattern as a staircase on the periodic table. Properties of both metals and nonmetals are found, and they are semiconductors. Some examples of this are silicon, boron, and arsenic. Other nonmetals are found on the top right side of the periodic table. They are poor conductors and they're often gases, such as oxygen, carbon, and nitrogen. Halogens are found in group 17. They're the most reactive nonmetals and form a -1 ion. Some examples include fluorine, chlorine, and iodine. Noble gases are found on the far right side. They're found in group 18. They're the least reactive and because they have their full outer shells, colorless and stable. Some examples include helium, neon, and argon. And finally are lanthanides and acetides. They're found in the bottom two rows, are shiny and often radioactive. They're used in magnets, lasers, and nuclear reactions. Two examples of lanthanides are called lanthanum and neodymium. Two examples of acetides are uranium and plutonium. In all, metals are on the left, nonmetals are on the right, and metalloids bridge in between them. Moving on to our last topic is periodic trends. Let's start with atomic radius, which is the distance from the nucleus to the outermost electron of an atom. Now here's what happens. As you move down a group, like from lithium to cesium, atoms get bigger. Why? Because each step down adds an extra energy level, or an electronic shell. That means that the outer electrons are further from the nucleus. There's also something called the shield effect, which increases. The inner electrons block the pull of the nucleus, letting outer electrons drift further away. But across a period, from left to right, atoms actually get smaller. That's because more protons are added to the nucleus, creating a stronger positive pull that pulls the electrons in tighter, shrinking the atom size. So the biggest atom are down at the left, like francium, and the smallest are up at the right, like helium. Next is ionization energy. That's the energy it takes to move an electron from an atom. Think of it this way. If an atom really wants to hold onto its electrons, it takes a lot of energy to remove one. Now, going down a group, ionization energy decreases. The atoms get bigger, electrons are farther from the nucleus, and the nucleus can't pull them in as tightly. So it's easier to just remove one. But moving across a period, ionization energy increases. The atoms are smaller and the nucleus has more protons, so it grabs onto electrons harder. So atoms on the right, like neon and fluorine, have very high ionization energies, while atoms on the bottom left, like francium and cesium, have very low ionization energies. Basically, small atoms equal strong holds equal high ionization energy, if that's easiest to remember. Now let's talk about electronegativity. This is how strongly an atom attracts shared electrons when it's bonded to another atom. As you move down a group, electronegativity decreases. That's because atoms get bigger, and their outer electrons are farther from the nucleus, so they can't pull bonding electrons very well. But as you move across a period, electronegativity increases. Atoms get smaller and the nucleus gets stronger, so if it can pull electrons from every atom more easily. The champion of electronegativity is fluorine. It's the most electron-hungry element on the periodic table. On the other hand, francium has the lowest electronegativity. It hardly pulls electrons at all. So again, small, strong atoms on the right have high electronegativity, while big, loose atoms on the left have a low electronegativity. Earlier I mentioned the shield effect, but what exactly is that? This is when the inner electrons block or shield the outer electrons from the full part of the nucleus. As you go down a group, atoms get more energy levels, which means more inner electrons, and that increases shielding. So the outer electrons feel less attraction to the nucleus. This makes atoms larger, easier to remove electrons from, and less able to attract electrons in bonds. In other words, more shielding equals bigger atoms and weaker pull. And that's your full review on the history of the atom, subatomic particles, chemical families, and periodic trends. If this helped you study, give it a thumbs up and comment which scientists made the biggest impact, and if you have any other questions. Make sure to subscribe and see you in the next one.